Welcome to the 6th lecture for Modern Aspects of Nuclear Chemistry. This lecture is on the chemistry of Americium and the chemistry of Curium. It's in two parts. The readings for both parts are the Americium chapter and Curium chapter of Chemistry of the Actinides and Transactinides. These will be linked on the webpage. Americium and Curium are combined into one lecture due to the similar chemical properties of these elements. We're going to cover Americium, and here's an example of Americium metal, and then move on to Curium, and here's some Curium oxide. This is Curium 244, short half-life, gives us this optical property. The first part will cover Americium, and we'll discuss nuclear properties of Americium, production of Americium isotopes, and then separation and purification of Americium. Part 2 will move on to cover the metallic state, compound solution chemistry, coordination chemistry of Americium, and then we'll repeat with Curium. We'll start off discussing Americium. So here's some information on the production of Americium isotopes. As we can see here, isotopes go from 232 to 247, where a number of the lighter isotopes are made from accelerator-based reactions, and then common isotopes such as 241 and 243 from multiple neutron capture. In this case, the buildup from plutonium-239 to 241. 241 will beta decay to Americium-241. As we've already alluded to, the 241 and 243 are the main isotopes of interest related to the chemistry of these elements. They have long half-lives. They can be produced in suitable quantities. The Americium-241 is a source for low-energy gammas. You've used it in calibration sources. It's a 59 keV gamma ray. There's also two alphas associated with this, and Americium-241 is employed in smoke detectors because of these alpha energies. Americium-241 is also good for making neutron sources, where the Americium-241 can be coated onto beryllium. The alpha from the Americium reacts with the beryllium, causing the production of a neutron. Americium-243 is from the further irradiation of plutonium. Carried further, you can build up to 242, capture to 243 plutonium, which undergoes beta decay. One other isotope, the Americium-242, has a very high neutron fission cross-section. In fact, you can get a critical mass of the Americium-242 of about 25 grams at 5 grams per liter. However, in order to achieve this, you would have to, in order to get some isotopically pure Americium-242, you would have to do some isotopic separation, because it's produced from the neutron activation of Americium-241, forming both the ground state and the metastable state. And we see that the fission cross-section is extremely large. The solution chemistry of Americium is similar to some of the earlier actinides. However, primarily it's thought of as trivalent. The trivalent oxidation state is easy to prepare. However, there is some exploration of divalent Americium based upon the behavior of some lanthanides. As we already stated, the trivalent solution is the dominant species in solution phases, relatively easy to prepare, dissolution of either the acid, either the metals or oxides in acids. The UV visible spectroscopy can be exploited to examine Americium speciation, and here's an example of the Americium-3 absorbance, relatively high molar absorptivity. The compounds tend to have high coordination water. The free Americium itself has around 10 inner spheres of water. So this is again typical of an actinide with high coordination environment. Americium-4 requires complexation to stabilize, so one must oxidize the 3 to the 4 and then work on the ability to stabilize the compound. And as an example, here's an absorbance spectra of Americium-4, which is 13 molar ammonia fluoride. So very non-standard solution. Other oxidation states of americium can be achieved. Americium 5, if you oxidize the americium 3 in near neutral solution. Ozone, hyperchlorate peroxide disulfate are suitable oxidizing agents. And the UV visible spectroscopy gives two peaks, one near 515, the other near 715, with reasonable molar absorptivities where the speciation of the americium 5 can be identified through the spectroscopy. Americium 6 can also be achieved. It can be from the oxidation of 3 with some more aggressive oxidizing agent, or 2 molar carbonate and ozone or oxidation at 1.3 volts. The absorbances are shown here at around 1,000 nanometers with a molar absorptivity of about 100. Americium 3 also undergoes luminescence. Remember, there was large absorption of americium at this 503. This can excite the electrons to states where they can be converted to other excited states. They can have a lifetime that's longer than your traditional de-excitation. They can be shifted, and you can see the emission bands at different energies. So this is a way of detecting americium and getting some more information about the speciation. One of the drawbacks of this is that the lifetime of the aqua ion is relatively short, 20 nanoseconds, extended to over 100 nanoseconds in D2O. This is much shorter than what was observed for curium, and much shorter still than what's observed for uranium. These multiple oxidation states of americium can undergo autoreduction. This is due to the radiolysis and formation of radicals that can change the oxidation states. This is particularly true if you have the higher oxidation states, which are notably unstable compared to the trivalent state. This also means that there will be a difference in this reduction behavior between americium-241, which has a shorter half-life and should have a faster reduction because of that. What is noticed about this is that the rate decreases with increased acid for perchloric and the sulfuric system. And there's also some disagreement in the literature on the role of the americium concentration in the autoreduction. What is known is that the reduction rates depend upon the type of acid, the acid concentration, and there are some stepwise mechanisms where it goes from the 6 to the 3, so it'll go from the 6 to the 5 to the 4 to the 3. And it also seems that the reduction from the 5 is slower than reduction that starts at the 6. Similar to this autoreduction, americium can also change oxidation state due to disproportionation. An example here is given for americium 4, where the americium 4 can disproportionate to the americium 3 and the 5. The 4 plus the 5 goes to the 3 plus the 6. So you can see if you start off with americium 4, you could actually populate a solution with the 4, the 3, the 5, and the 6 over time. Americium 5 also undergoes disproportionation, where it'll go to the americium 3 and the americium 6. The solution conditions can obviously impact the oxidation state stability and the influence of disproportionation. For instance, with this reaction with the americium 5, since it needs relatively high concentration, so 3 americium 5s in this reaction, storing a solution of americium 5 at lower concentration of americium should stabilize the solution. And then here's some of the disproportionation kinetics, where we see the relative distribution of the different americium oxidation states, the 3, the 5 decreasing, and the 6 increasing and decreasing over time. In 5 molar perchloric and 5 molar HCl, we certainly see some differences in the HCl where it's driven to the trivalent americium state more rapidly than in the perchloric system. As we already stated, americium undergoes oxidation. by a number of compounds. The redox kinetics, or the oxidation kinetics, of americium-3 have been evaluated with peroxide disulfate. And this oxidant will bring americium to the 6. There are some limits to the applicability of this system. In acid above about 0.3 molar, you get decomposition of the peroxide disulfate. So it does have some limited capabilities at those higher acid concentrations. It is found that the rates of oxidation are dependent upon temperature, nitric acid, and then which oxidizing agent one is using. In carbonate systems, the oxidation can proceeds through americium-5. The rate for the formation of americium-5 is found to be proportional to the oxidant. And kinetics of americium-3 oxidation has been examined. Some data shown here for the kinetics of americium-3 oxidation peroxide disulfate as a function of different nitric acid concentrations. And as we see, as we increase the nitric acid concentration, the rate decreases. A, which has the lowest nitric acid concentration examined in this work, has the fastest reduction. The reduction of americium-6 has also been examined. The kinetics for the reduction of americium-6 in perchlorate by hydrogen peroxide is first order with the peroxide and americium, bringing the 6 to the 5 with the generation of acid and water. The reduction of americium-6 by neptunium is first order with the americium-6 and the neptunium-5. So the speciation of oxidized states of americium can also be influenced by if there's other actinides in the solution. Oxalic acid reduces the americium-6 to equimolar americium-3 and americium-5. In a number of these conditions, you tend not to see the stabilization of the americium-4, but other americium oxidation states are evident. Americium-5 reduction has been examined and it reduces to the 3 in sodium hydroxide solutions. The reduction is reduced with sulfur compounds, as shown here. Both neptunium-4 and 5 have an influence on the americium-5 reduction, and this has been examined in both acidic and carbonate solutions. With uranium-4 also, the oxidation of uranium-4 to the 6, followed by the reduction of the americium-5 to the 3, has also been examined with uranium in carbonate. The solution chemistry of americium can also be complicated by radiolysis. The energy from the alpha decay releases enough energy into the system to form species that will influence the redox state of the americium. In nitric acid, for instance, nitrous can be formed. In perchlorate, a number of species can be formed. All these influence the resulting speciation and oxidation state of americium. And you'll see differences between the 241 and 243 as was discussed earlier in the lecture. The complexation chemistry for americium has primarily been explored for americium-3. Strength of ligands are general trends with hard acids and hard base reactions. The stabilities of the resulting americium-3 solutions are similar to the trivalent lanthanides. There's some enhanced stability due to the 5f electron behavior in the americium, but this is an indication that if you could not find data for americium compounds, one could evaluate trivalent lanthanide compounds of similar ligand complexes to get an idea of how americium would behave. And here's an example of some complexation constant, Gibbs free energy, and enthalpy for a number of americium solutions, hydroxides, carbonates, fluorides, chlorides, etc., that are listed here for both solution and solid phase species. An important solution species of americium is, of course, the hydrolysis. The mono, di, and trihydroxide species have been examined. Americium-5 appears to have two species, the mono and dihydroxide. And here's an example of some americium speciation from the CHESS database. 1 millimole of americium. You start to get a decrease of the free americium concentration around pH 6, where the formation of the americium trihydroxide at the higher pHs. In the presence of carbonate, as shown here, we see in 1 millimole of americium, 1 millimole carbonate, the mixed americium hydroxy carbonate species dominates from around pH 5.5 to around pH 8.5. These carbonate species were examined by spectroscopy, and these mixed species is demonstrated can be a very important dominant species. Americium-4 carbonates have also been examined with the pentacarbonate species complexation constant evaluated, and the solubility of americium-5 carbonates have also been evaluated. The complexation of americium-3 with organic ligands have been evaluated. There's a general trend, as shown here, where the complexation constant increases with the number of available coordination sites. And the general trend is the more coordination sites, the higher the complexation constant. You see these are for the beta 1, which is the 1,1 complex, and then the 1,2 complex is the squares. We see that there's a general trend from here to 8. However, there are some exceptions, and that could be due to steric effects or the correct coordination environment. The fundamental chemistry that we just described on americium can be useful for separations. As we know, solvent extractions are useful separations techniques, with tributyl phosphate being a major workhorse in the nuclear fuel cycle. We know that in high acid concentrations, americium does not separate. However, in neutral or low acidic solutions with high nitrate, tributyl phosphate can be used to separate americium, extract americium into the organic phase. If americium is oxidized to the 6th state, you can get separations and extraction in 1 molar nitric acid. You can get good separations from neodymium due to the oxidation. And studies have shown using some polyoxymetallates, such as what's shown here, to stabilize the americium-6 so that it can be separated. There's other separations, dibutyl butyl phosphonate. It's similar functional group to tributyl phosphate, and it's shown to have a stronger extractant for americium than tributyl phosphate. Trialkyl phosphine oxides, as shown here, we increase the basicity of the P double bond O group from tributyl phosphate to the dibutyl butyl phosphonate to this molecule here, so that we can increase the extraction of americium. Americium in curium is extracted from 1 to 2 molar nitric acid with this ligand. And studies have shown with 30% TRPOs in kerosene, americium, curium, and the trivalent, tetravalent neptunium, plutonium, hexavalent uranium can be extracted. And these were done with C6 and C8 functional groups on the TRPO. Other solvent extractions that are used for americium includes HDEHP. This is part of the Tall-Speak process, which you can look at. You can look up in some links on the separations page, and will be part of the separations presentation. Tall-Speak uses HDEHP, nitric acid, DTPA, and lactic acid. So this organic, the HDEHP, is shown here. It goes into the organic phase. The DTPA, diethylene triamine pentacetic acid, remains in the aqueous phase, and lactic acid is used as a buffer. CMPO has also been used, the ligand shown here, and this is part of the Truex process, which is used for fission product extractions. So separation from the lanthanides and actinides from the fission products. And this it also employs tributyl phosphate, the CMPO, oxalic acid, lactic acid, again as a buffer, and DTPA. Other extractants that have been evaluated include some amine salts. They've been evaluated in low acid, high nitrate, or chloride solutions. Common extractant is called this aliquot 336, which is shown here. This is useful for extracting in low acid and high salt solutions, and you get an extraction sequence of curium being less than californium, americium, and einsteinium. This has been examined at Argonne National Lab for process separations involving americium, the aliquot 336. There's also a number of amide extractants The amide functional group is shown here. This is the basis of a process that's been evaluated in Europe called the Diamex process, where this maleimide has been used as part of the Diamex process, and in 3 to 4 molar nitric acids, now we're at higher acid concentrations, you get a selective extraction of americium over neodymium. Other separations have been included separations of americium from the lanthanides with an extraction reaction. An example that's shown here is with Cyanex 301. This compound is shown here. This ligand is stable in acid. And as an example shown here, there's distributions of the trivalent americium and the trivalent lanthanides. In 1 molar Cyanex, that's around 16 mole percent of Cyanex 301 in heptane. So you can use this ligand to achieve selective separations, and it's driven by the soft donor properties of these ligands. Irradiation studies have also been performed with phosphorus compounds, and extractions start to become problematic at relatively high doses. And this has led to the synthesis and characterization study of other phosphonic acids that tend to be less sensitive to the acid concentration, less sensitive to radiation and hydrolysis effects. However, most of these ligands operate with synergistic extractions, so you tend to have more than one ligand in the solvent system. So, for example, these diphosphonic acids will work with tributyl phosphate, trioctylphosphine oxide, or tributyl phosphine oxide. The aqueous phases are between 0.1 and 1 molar. So the acidity isn't as high as some of the extractants that we saw on the previous page, but they're in a regime which is relatively easy to control. Separation of americium and curium has been examined with ion exchange, and much of this exploits the fact that lithium chloride has shown to separate the actinides from the lanthanides. As shown here, here's an example of 10 molar lithium chloride separation. Distribution coefficients on Dowex resin, we see that the lanthanides have a very low distribution coefficients and the actinides a much higher distribution coefficient. So ion exchange has been used in 2 tracer type levels, one using a displacement complexing chromatography. It involves a 2 ligand system, 2 metals that act as competing cations. You use the slight differences in the complexation between americium and curium to achieve a separation. This method is somewhat cumbersome and complex, can be used on a small scale, but not particularly suitable to large-scale separations. Another route for separating americium, curium, and the lanthanides is to sorb the material to a cation exchange resin at pH 2. And separation of curium from americium was achieved by using a relatively weak phosphonic acid solution, this ethylene diamine tetramethylphosphonic acid, at pH 3.4 in 0.1 molar sodium nitrate. And he achieved a separation factor of 1.4. Not a particularly high separation factor, but one that could be used to achieve a separation if enough effort is put into the system. Large-scale gram quantity separation of americium curium has been performed using cation and anion exchange, and it's using ligands such as alpha-hydroxy isobutyrate, which we showed was used in the discovery of these elements to separate the lanthanides, and they also are useful in separating the actinides. DTPA can also be used as an organic ligand in this case, where the metal ions are sorbed to the resin and selectively removed with the acids. The eluent can be varied using a gradient of methanol and nitric acid. Best separations were achieved under high pressure. Separation factors can be as great as 400, much larger than the separation factor as we previously discussed. And the use of high pressure increases the theoretical plates of the system, enhancing the separation. Extraction chromatography is also performed with americium. One can think of extraction chromatography as combining solvent extraction and ion exchange, where there's a mobile liquid phase, generally the aqueous phase, and a stationary liquid phase, generally represented as the organic. So for the Americium work, you can apply studies that were performed with the organic ligands such as HDEHP, CMPO, aliquot 336, and these are the basis of ichrome resins. There are some limitations in the solution depending upon what sort of ligands you have. These are mainly based upon the fact that these ligands will coordinate strongly with the metal ion, preventing interaction with the resin. There is another resin from ichrome which uses ethylhexyl methane diphosphonic acid on an inert support, and this extracts trivalent, tetravalent, and hexavalent actinides. In fact, this resin binds those metal ions so strongly that there's a need to remove the organics from the support in order to liberate the metal ions from the column. There's also variations of support. The ichrome resins are just hydrophobic interactions which keep the resins on the column. One can also covalently bond molecules to silica, and then some of these sites that it can be covalently bonded, you can coat the particles with ferromagnetic make them have ferromagnetic properties. So after separation, you can use a magnetic field to separate the resins. You pull out the resins from the solution, thereby separating out any extracted americium. Other aqueous separation processes for americium include precipitation. This is driven by the formation of insoluble americium species, everywhere from trivalent to the pentavalent americium, here shown as the carbonate. Particularly this species, where americium can be oxidized to the +5, where curium cannot be oxidized, is a route for separating americium from curium. Americium can also be separated from the lanthanides by oxalate precipitation, where particularly the use of dimethyl oxalate as a route for this selective method of precipitation to achieve 50% lanthanide rejection, with only 4% americium rejection. So in this case, the precipitate winds up being enriched in the americium. Other routes for precipitation include americium-6 and the precipitation of curium-3. So in this route, the hexavalent state is soluble, where curium, as a trivalent, could be precipitated by such species as the fluoride. There's also pyrochemical processes for separating americium, particularly from plutonium, where if in a molten salt system oxygen is introduced, plutonium dioxide forms and precipitates. And americium can also be partitioned between liquid bismuth or aluminum and molten salts. I think this could be thought of as a solvent extraction system, where the solvents are molten salt and a liquid metal. Distribution coefficients of 2 for the aluminum system have been achieved for americium. Volatility-based separations of americium from plutonium can also be achieved by exploiting the the plutonium hexafluoride, which is volatile. So the formation of this fluoride species in a fluoride salt, so you start with the tetrafluoride of plutonium, bring it to the hexafluoride state, and achieve separation from americium by the volatilization of the plutonium species. This completes the first part of Lecture 6, the chemistry of americium and curium, where this lecture focused on the americium nuclear properties, production of americium isotopes, and separation and purification of americium. Part 2 will cover metallic state, compound solution chemistry, coordination chemistry of americium, and then repeat all these lecture topics for curium. Please proceed to Part 2.